This is very new work. It's work in progress, and actually I'm talking about this for the first time today. But I think it's something that we should consider. I think it's something which looks to me as having a disruptive quality to the way how we think about networks of spiking neurons. So learning to learn is in principle an old topic. Some people call it meta-learning. I think it's synonymous. And it has been discussed for decades in papers in neuroscience, cognitive science, and also in machine learning. But only more recently, when also sufficient computational power is around and some newer ideas from very bright people, it has become an important tool in machine learning. In particular, is booming there since 2016. But so far, it has, as far as I can see, never been applied to networks of spiking neurons or to neuromorphic devices. And I think there is a lot of potential, and I want to discuss this here. So I want to review here quickly also this standard learning to learn framework, assuming you may not be familiar with this, because I think it's an important really change of perspective of learning, which makes a big difference. So instead of learning a single task, one always focuses on families of learning tasks. So this could, for example, be all the learning tasks that the device is likely to meet during its lifetime, right? So of course, nobody knows this. You have to make a model for this then, but including kind of taking into account kind of really adversarial situations where really this device has to be ready for new things then. And this family here plays a role because altogether this learning to learn takes place on two levels of learning, as the name suggests. Then you see an outer loop and optimization algorithms. And this optimization algorithm, or it could also be a learning algorithm in itself, controls a certain set of so-called hyperparameters. Theta always right for this, which are parameters of the learning of the network. I will discuss examples in a moment. There could rule certain parameters we don't know, but also weights and other things. And so this is now a neural network, a spiking neural network always in this talk, and it gets a task drawn randomly from this family, and then it has to learn it, and the fitness of this learning process of the spiking neural network is considered by this outer loop, and the outer loop then tries to optimize this function, increase fitnesses. And so this is kind of a very loose framework. When you want to get something out of this, it's a little bit an art then. You have to define the family F in a way that the result that comes out is what you want to have. You also have to define the fitness function in a way that it really provides what you want to have. And also you have to choose this network size and architecture in the right way. And you have to really choose what the set of hyperparameters is then. So therefore, this is not a single algorithm. It's really a kind of a large family of algorithms. It's more design setup then. Or you could view it also as a very abstract, loosely as a programming language where we program the result in terms of a number of design decisions then at the beginning then. And then the testing also is done in a completely different way than standard in machine learning. You all know is you test on new examples, but from the same learning task. Here, you draw a random learning task, in general, a new learning task, then if it's infinitely large, and you test on a new learning task then. So this is, I think, an important difference. So now when we think for example, about a concrete neuromorphic device, for example, neuromorphic chip, then for example, when F thinks about chipping is Louis, after doing some parameter determination, then maybe they have to define here F as a family of learning tasks this chip is likely to encounter during its lifetime then. The hyperparameters, one could, for example, think about choosing all those aspects of learning in this neuromorphic device N, in this inner loop, about which we are not sure, where we don't have clear mathematical principles. So this could be the architecture of N, the time constants, and other physical parameters of this neuromorphic device, some or all of its synaptic weights, the plasticity rules. There could be different rules used in different parts of the networks, also at different times. And also a curriculum or learning rates could be specified through these hyperparameters. So in principle, now, this overall framework is extremely general. It's not even forces you whether you want to think about supervised learning, unsupervised, or reinforcement learning, and you can mix them also for the inner loop and outer loop in any way you want to. And in our first proofs of concept, which I will quickly discuss here, we took benchmark tasks which were in the published literature, 2 key papers which applied learning to learn for artificial neural networks, more specifically recurrent neural networks, and really specifically recurrent LSTM networks. And so here particularly I recommend to look at this paper from Botvinnik lab now at Google DeepMind in Oxford, formerly professor of neuroscience at Princeton, Wang et al., learning to reinforcement learn, and then also a much older paper by Hochreiter, Younger, and Conwell. I will discuss later for supervised learning their paradigm and see to what extent spiking neural networks can duplicate some of their results. So first I will discuss this learning to learn from rewards, more kind of looking at this benchmark task from Wang et al. And here, it's a typical reinforcement learning environment. The agent is incorporated, is really the neural network, spiking neural network is the agent. It outputs actions, and then it gets what the current state is and the reward then. And the fitness is typically then chosen as a sum of rewards, but you can also put in other things, which, for example, give an incentive to learn fast or something like this then. And in addition, one key element, which was already, in principle, Hochreiter et al., but also in Wang et al., is that you give at each time step not only the current state, but you give it also the previous reward, the reward for the preceding time step, and also the action it has taken at the preceding time step. And this spiking neural network should then output a policy, what to do, what action now to perform then, and also value function, predict the value of this current state xt then. And now an interesting situation, which is at first really surprising, is that one can choose also here include the weights of this neural network in the inner loop all into the hyperparameters, which is very strange because then you have to ask what does this inner loop neural network, this spike neural networks, how can it learn something? Because when you learn something, you have to accumulate information and modify it during learning. And we are just so brainwashed that we think synaptic weights must be those places where this takes place. But in principle, neural network can have many other kind of dynamic states on different time scales where it maintains these variables then. And so this was already discovered long ago by Hochreiter et al. And Conwell before that. And this is now a new type of learning algorithms also, therefore, that we're starting to look at. And one key element which is needed to port some of the results from recurrent artificial neural networks into spiking neural networks is that we need a replacement for these LSTM modules, which are present in virtually all results in current machine learning when they apply recurrent artificial neural networks. And so, as you know, these are kind of well-tuned kind of working memory modules, which kind of trainable access and readouts from these memory modules. And you need them, obviously, for any tasks which require computation and learning on a time scale, time series. And so this has been open for quite some while now, how with a spiking neural network we can create something like this. And so this is something we came across a nice way of doing this. We're at the moment writing this down then. I don't want to discuss this module here today. But it's something which is actually both, I think, biologically quite plausible if one cares about this, and I think it can also be easily implemented on a neuromorphic chip then. So now that this weight vector of this spiking neural network no longer has to be free for really accumulating values counter during learning. You can use it in a different way, and the paradigm is here, or one paradigm, it's not a dogma, one can do it also differently, is that the weight vector actually of the spike neural network encodes the reinforcement learning algorithm. So this is my first thesis, really kind of a jump in types, that weights can encode an algorithm. But I think about it this way: a learning algorithm is simply a computational kind of rule then. When you have current values of parameters and you get this new data, how do you change these values? So this is simply a computational function. It's typically a smooth function. Any smooth function can be approximated by a neural network, and so therefore a neural network can now compute these learning rules in many different ways and represent them. And by changing the weights of such a neural network, you can modify these learning rules then. And so suddenly we have now kind of not only a universal computation capability, but a universal learning capability or learning algorithm representation capability if you think about neural networks in this way. So this is discovered long ago in artificial neural networks, and I just here want to point out to these fascinating consequences that this has for spiking neural networks. And then also Botvinnik discussed recently also that he has submitted a paper where they argue actually that their data from neuroscience, particularly about the prefrontal cortex, that argue that there are aspects of this type of learning and maintaining results of learning, not in weights, through synaptic plasticity, that this is something which may take in the brain, may take place in the brain. As you know, also from other perspective, synapse physiologists have argued for a long time that SATP is not likely to be kind of really the main engine for doing fast learning then. So now we have applied this as a first proof of concept to this high-current DLS chip. Johannes Schemmel and Karl-Heinz Meyer, the inventors, talked about this briefly. So this is a catch. And what is new there is, in addition to synapses and neurons, you have a digital processor, a plasticity processor, and this one has working memory. So actually there we don't really have to look for other spike-based or so working memories. We can relatively use this registers on this plasticity processor. And so at the moment, there's only a small chip of this type available with 32 neurons. But we wanted to use it because this is now the precursor of a much larger chip then, and in the end it will be used for the wafer scale integration in the Human Brain Project and to build large spike-based neuromorphic system then. So in this application to this chip, we let this hyperparameters theta control both physical parameters of this chip, but also detail of the learning rules. The hardware was then applied TD lambda to learn the Q function of a reward-based learning task. And so we applied this to two families of reward-based learning tasks. One was navigation to a goal in random mazes. So these were mazes of this size then, but randomly kind of drawn how they're connected. And the goal was to reach the learning goal was to reach this goal from any position in the maze. And then we also considered simply the family of random Markov decision processes of a given size then. And the key element we wanted to tease out then, simply as a proof of concept, is that these neuromorphic devices can exhibit transfer learning capability, which simply arises from the family of having many similar other tasks learned previously, although different random MDPs may not really have so much intrinsic similarity in what is a good policy, but they have something in common then. And so therefore, kind of the nice aspect of this method, through sufficiently long training in the outer loop, you can force these spiking neural networks in the inner loop to extract these common aspects of all these random MDPs of a given size, or all these mazes there. They have something in common there. And so this is something I'm quite excited about, that the spiking neural networks really kind of become able to abstract something and apply this abstract knowledge to learning a new task much faster than without having this experience before and this abstract knowledge. Then just from the kind of algorithmic side, it turns out also here now we applied, this is a non-differentiable fitness function then, so we applied then one of these very nice new strategies, the so-called evolution strategy from the Google, no, this is on the Open AI lab then published last year. This is something which is now combines policy gradient together with an empirical estimate of this gradient. And it turns out when we now apply this now to many different individual Markov decision processes, kind of then and let this chip learn for each of these individuals, we see then that the fitness goes up here for the red curve, which is ES, quite fast, and whereas for kind of standard algorithm, which I had thought these are maybe the best general nonlinear optimization algorithms like simulator annealing, it stayed pretty much flat then. And so this is not a general rule. This is different for every family of learning tasks, every network. But I think what we need and will probably acquire during next year is simply a lot of algorithmic know-how, which type of algorithms to use for which type of learning to learn setup then. So then also we had done a number of also software simulations of simulated networks of spiky neurons. And so I want to just discuss this example because it's something that I find really nice then. And it's again something we looked at a family of learning tasks, which is in a sense really weird or mean. This comes from the Wang et al. Paper. They used this as a kind of benchmark test. So assume you have an 11-arm bandit, and the 11th arm encodes indirectly the address of that one of the other 10 arms that has the highest reward probability. Namely, this 11th arm gives a reward between 0 and 1, and you have to multiply this number by 10. This gives you the address of the other 10 arms, which gives you the highest reward then. So once we see it's of course trivial, and now it's trivial to write a program which kind of executes this simple policy. But look, this is a stupid recurrent spiking neural networks, and I wouldn't even know how to get a spiking neural network to execute any program that I like it to execute. And so therefore, I find it quite nice that we see here in this proof of concept that spiking neural networks can learn and can be made really to execute a program then. And also now, this is, I think, interesting. So here you see the count of optimal pulls on the y-axis, and the x-axis is the number of training opposites, so the number of these bandits from this family which have been drawn here. And you see, after about 500,000 episodes, suddenly the spiking neural networks figures out what is a good policy. And there's a drastic jump in performance, and then it still somewhat improves. We have to look at what exactly is still improved here there. And so this is something which gave for me really kind of a very positive feeling that we may be able to tweak out of spiking neural networks really previously not seen functionality by just also setting it up in the right way, but also being patient enough to waiting and optimizing here for enough training episodes. I quickly also want to discuss, how many minutes do I have? Okay, pretty fast. So learning to learn from a teacher, which is quite exciting because it addresses the issue of backprop and spiking neural networks. Because this is, we look at here at a different type of task, which is taken from the Hochreiter paper. The family is simply the set of all quadratic functions. You get as input two numbers, x1 and x2, and you're supposed to output g of x1, x2 then. And so for every learning episode, this parameters change, so different quadratic function then. So the question is whether you can get these spiking neural networks to figure out a good strategy for learning any new quadratic function, making use of its history that it has learned lots of other previous quadratic functions then. And so here also, the interesting situation is that we use here, in this case, also the same setup as Hochreiter et al., that here, the spiking neural network is not allowed to change its weight for learning a particular quadratic function then. So therefore, its learning algorithm has to be fully encoded in the weights then, and other dynamic kind of variables are used for maintaining information while learning a particular function then. And so therefore, as I mentioned before, since this weight vector of this spiking neural network encodes its supervised learning strategy, one sees now that the spiking neural network has a really very large reservoir of potential learning rules it can use then. And so this goes far beyond backprop or any concrete algorithm. And so this is, I think, something which I think is a good approach then, that we don't get stuck with kind of seemingly brain data, how brains learn. And I think neuroscientists say most of the things are out there, how brains exactly learn then. And so therefore we also know as theoreticians and engineers, we can simply look for the best learning algorithms for a family of learning tasks and not to be over kind of constrained by what we think is really the way how the brain does it. And so now this is now something which works quite well then. And so therefore, and this network learns pretty fast then for a new quadratic function to learn this. And so this is here a similar learning cave. In this case, the arrow is drawn, the arrow for this quadratic function, so the difference between the guessed output and the actual output of the unknown quadratic function. So here also we see it makes no drastic progress at the beginning. This is just when it figures out the output values have to be between 0.2 and 0.8 then. So it gave previously two large output values. And then this is here after 10 iterations of quadratic functions, after 2,000, having learned 2,000 quadratic function, and here having learned 5,000 quadratic function. And always this is here, the target value was supposed to output for this current quadratic function, and this was the actual output. And we probably, if we continue this, this gets closer and closer to this line here then. So my summary is that I think there's a good chance that this proof of concept can be also ported to much more ambitious tasks. And in particular also I mentioned that if we give some LSTM-like modules into spiking neural networks, we can boost their computation power, but also learning capability. And then also I presented briefly that learning to learn from rewards, and so therefore transfer learning capability can be ported to a neuromorphic chip with learning capability. And I think this will be important that in the future this is done for lots of neuromorphic devices that they carry out transfer learning, that they really have in the factory or they acquired in the early parts of their life a lot of really accumulated recipes how to learn things fast and well, then that they don't start tabula rasa at the customer when in the store then. And so now what is really needing now is we get this spiking neural networks, and we know they do their job very well. They have gone through millions of optimization iterations. Now a really interesting reverse engineering task is in front of us. We have to understand how they do this, right? So just for curiosity, but I think there are some new recipes, new tricks to be learned, and both the architecture and the modules and how different modules are put together then. And so this is, I think, very parallel to this work in neuroscience, where people wonder, why do you have in a cortical column lamina? Why do you have so many different types of neurons? Why do you have specific connectivity probabilities for different types of neurons then? And I think we get here, at least as an analogy, in this way, also a parallel task then. And I think we can benefit from applying methods from neuroscience, but also vice versa, because here we have now this spiking neural network in our hand. We can do many experiments which so far were not possible in neuroscience. And we can then possibly find out which experiments for reverse engineering really give you a lot of information about the underlying structure, why then, how the network does this then. I think that applying this method has large potential to revolutionize the design of recurrent neural networks for concrete computation, as well as the design of learning algorithms for recurrent neural networks can be completely rethought then. And in particular, I think what we're aiming at for the coming year and years is, I think we can now produce spiking neural networks which can much more also learn to do well using abstract knowledge, that they can follow rules, they can integrate episodic memory with other information and carry out symbolic computation and reasoning. Thank you.
Thank you, Wolfgang. Very cool work. Yeah,
question?
very nice work, Wolfgang. So one question is I have is on the meta learning in the reinforcement case. The meta learning in the reinforcement learning example that you gave, and so there's kind of two different types of transfer between tasks. So one is if so you, as I understood it, you generate random mazes, and then it was, I guess, a navigation task in these random mazes. But you could also think of actually different targets in the same environment. So there's kind of this transfer where you need to become an expert of a particular environment, but then your target changes in that environment. So in order to capture that in a model, you would need to kind of separate out the model about the environment and the model about the task. So how is this working in your spiking neural network?
I think in principle, I think you sketched a wonderful new family of learning tasks. So I think one can really evoke this capability by just setting it up in a different way, right? Defining out this family, and if you want to fix maze by different positions of the goals. And actually, right now, we also, to integrate episodic memory, we want that it learns to go back to the position it started with then. So therefore, it has to go to the goal and then remember where it came from and go back to this initial position. Then I think this will also work.
I mean, for this transfer, actually, in the same environment, actually, just information-driven exploration has been shown also by some of the early papers of Schmidhuber, and also we did some work that actually just exploration helps you a lot to be.
Yeah, I think it's actually, I forgot not to say this, I think the main advantage from this learning to learn experience is that they have really very clever exploration strategies, which a greedy strategy would not really want to do then. They know how long to explore and what to explore then. And also should say then we benefit really here from really wonderful work on the algorithmic side from Google DeepMind now, and it's basically the same industrial strengths reinforcement learning algorithm which have been used for AlphaGo and others. And it's nice to see that we can use this machinery also for improving spiking neural networks performance.
Right. This is very, very cool stuff. One of the challenges that we think of in neuromorphic applications is getting the spiking information, since you have spikes, if you can get the information into a temporal code, so the more, when the spike happens, there are power savings, obviously, as opposed to just purely in which spikes occur when, where. So have you thought about how you can use this method to kind of bias the implementation towards maybe sparser temporal coding regimes if you're using neuromorphic hardware?
Yeah, it's a great question. So we wanted to have the spike networks to use sparse activity then, which simply was put into the fitness function. And I think it's now a part of this reverse engineering job to figure out what neural codes are used in these well-working networks. It looks to me at the moment that there's more kind of spatial temporal spike patterns. We typically have set it up that they can't work with rate codes then. And so this is something, as you're indicating, something we really need. We need to have kind of working paradigms, kind of which codes work well for certain types of computations then. And one shouldn't look at just one or two different kind of codes, but simply see what codes are good for what types of or ranges of tasks then.
Okay, thank you, Wolfgang.